Good morning. Welcome to PhotoTech Talk number 25. I'd like to introduce Andrey Filippov, President and founder of Elphel. Andrey develops open source cameras and is here to talk about his cameras and the technology and applications. He will answer questions. If there are any questions that are specific to Google-related projects, we'd like to save those to the end of the talk. Otherwise, feel free to ask questions during the talk. Thank you.
Thank you. Okay, so I'll start with a little of the history of our company, so I started in 2001. After watching, I didn't know anything about Linux or free software, because I'm mostly a hardware guy, and so I used Windows system and Windows tools for my work. And my colleagues at the company where I worked for needed to connect several FireWire video cameras to acquire just one shot, one frame from each of them, but at the same time. And so they used some kind of small PC-104 computer boards. Yeah, and so they started with Windows C, then embedded in C. There was no XP at that time. And they didn't have any problems to connect to install this system, to connect one camera and to get video from it. But when they tried to connect more than one, and they needed 4 or better 8, so just to get one frame from each of them, then they couldn't do it. They contacted Microsoft support, and there was no solution. It was like a concrete wall, so you can get to the point, but not farther. And then I watched them spending several weeks installing. Now I know it was Debian, but I didn't heard anything, so I just Debian logo. It took them several weeks to make it run on this hardware, but after this, and they also didn't have any ready-to-use solution for multiple cameras. But when everything was running, just in a couple of days, they wrote a little of code and were able to connect 4 cameras at once. So that was kind of when I noticed this, I decided that okay, this probably it's so powerful, it's the way to go. So I quit my job and started a company to build hardware around Linux. And so first I looked for so what's the minimal hardware I can run normal, not UC Linux, but normal Linux, and something that's easy to use, because I had zero experience in Linux or Unix. And I decided to go with Axis processors. They run kind of normal Linux. They have a nice hardware feature that it has hardwired network bootloader. So to program Flash, you don't need to have any special connectors or pre-programmed chips. And if you update the firmware and screw up during reflashing, you always can get back and restore it. And other thing it was that from Axis I could get download SDK and all documentation from one place. Then my friend installed me Linux on my computer, because it was 2001. It wasn't so easy, and I didn't know any commands. I asked him how it will be dir in Linux. Yeah, and in 3 months I had a camera that could serve JPEG images. And yeah, it was really amazed because before it took me like half a year to implement SCSI interface in some embedded camera, because it was all assembly language. with this one, I printed thick manual with the instruction codes of the processor, but later I never used it because it was kind of so efficient to use mostly existing software, maybe make some porting, but it was even with no prior knowledge of Unix system, I could port this JPEG libraries and make them run with the. But 2001, it was a pretty hard time here. So when I quit my job, and I counted on my former company where I worked for that I will be their subcontractor, but it didn't work on the relations. And so for several years, it was really difficult to survive because I was making the gated intensified camera module intended to use by my former employer. And so it wasn't some product that is of general use. And yeah, so that while I still had some credit card limits on and could survive for some time, I started to work on the camera because there was some article in Linux devices about I wrote about this first camera. It got to Slashdot, and many people were interested in more general use cameras. So then next project was to make a camera that can be competitive even without image intensifier with high speed shutter, but just like a network camera. So kind of lower cost. And so for this project, I decided to go with the first one. It had some one-time programmable FPGA only to control the internal functions of the camera, like control interface to sensor, to DMA, to transfer data to the system memory, but there was no real processing in the FPGA. So next project, I decided to try a new thing for me because I never used it before, reconfigurable FPGA. Xilinx, I was comparing Xilinx and Altera. They were about the same kind of performance, but Altera, they had free for download. Also, both companies have free for download software, but Altera had a 3-month license. So you download for 3 months, it will work. But what will happen in 3 months? Maybe you will not be able to use your code anymore. So Xilinx, at least there was no expiration time. So maybe they will change their policy in the future, and I will not be able to upgrade. But at least I will be able to support my code that's already running. And then, with this reconfigurable FPGA. So I added dedicated memory to work with FPGA because memory, there are small banks of memory on chip in FPGA, but when you work with images, it's definitely not enough. So it was additional SDRAM memory for the frame storage and buffering. And so the first project was just to implement JPEG compression. And it turned out that so this reconfigurable FPGA, they're pretty fast. And this compressor, so I could get like was it then 1.3 megapixel at 1080 by 1024 at 15 frames per second. JPEG compression. Then with the newer FPGAs, with mostly the same code, it will be twice higher. Yeah. So it was next year, and there was again article in Linux devices, and it also got to Slashdot. And pretty soon after this, it was published. I got a call from one large company, and they said that, okay, you have really nice camera, but it's not doing exactly what we need. because we need high resolution, maybe not that high speed, but like 10 or more megapixels. And we tried, actually not we tried, we're now evaluating Kodak and Canon cameras, and each of them is close, but not exactly what we need. At first, it kind of scared me. I didn't take it seriously because, okay, I'm a one-man company, and I can't really compete with Kodak or Canon. I can't manufacture at the similar price, and so I didn't take it seriously. But in a month, the same person called me again, and yeah, so. It doesn't work as we want with these big companies. So, okay, can you make the camera? Yeah, and so then I started to work on this new camera project. It reused the camera what I had before, because I already knew that the sensors, they appear new sensors, and so to increase the kind of lifetime of the product, I split it into computer board and sensor board. So sensor board is just a minimal circuitry around the sensor, and all the rest was on this computer board. So it was processor, memory, and FPGA with its own memory, and network interface. So this was kind of computer part, and actually we have some. It's a newer camera, but it's about the same. So in this lower frame rate but high resolution camera, we just used the same processor board, and I had to, because it was CCD sensor, it needs more support circuitry, so it was kind of larger sensor board, but it still reused the same compressor, the same processor board. And actually, this board has some processor. It has network Mac on chip, and it had, at the time, it had some performance limitation because it didn't have hardware checksum calculation. So to increase frame rate, we put two of the boards in the cameras. Just each board was reading half of the image. So that was kind of strange camera with two network connectors, and each were getting half of the image. But that simplified development, because a lot of FPGA code and software code, it was reused in this different camera. So at that point, I still could handle it myself to design hardware and FPGA code and software. Only after this project proved successful and started to pay off, then we were able to increase the company size to have more developers working on it. And so then there were, as I was preserving the same form factor of the camera, but as memory density went up, FPGA density also went up. So when we made the next camera, so it was third generation with a larger memory and FPGA, and that camera was capable of running video compression as 1280 by 1024, 30 frames per second. With this camera, I also implemented, it's not complete implementation of Ogg Theora codec, because when I was going to implement MPEG, but when I was trying to download documentation on this, I found that it's there's so complicated licensing mechanism for this for MPEG, especially for MPEG 4, I think they now simplified it, but at that time, license should, it wasn't just for the device, but also for each megabyte or second of the stream. So it was something not really compatible with the free design, because in our cameras, everything is under GPL license. And we do not offer any alternative commercial licenses, like there's some other IP camera companies asked if we can sell them this design. No, we do not sell. It's only under GPL. It was GPL2. Now we're in the process of updating all the headers for GPL3. So it will be GPL3 shortly. And yeah, so then it was nice to have Octheore because it's royalty free. It still uses patent technology, but it's royalty free, so anybody can use it for any purpose. And in this implementation, I do not have motion compensation. So it's designed mostly for the camera that doesn't move, and most of the background doesn't change. So, and probably with the current FPGA size, it's all what I could do. I hope Xilinx will soon release Spartan 4 or using 65 nanometer technology, what they have in Virtex now, and that will be enough to implement to make full implementation of Octheore with motion compensation. That will be good for just other video applications when the camera moves, when there are more moving objects, and have lower frame rate. With this, so now it's Axis finally upgraded their processor. So this year we made the next generation using Axis E-Trex FS. It's about three times higher performance. Also, we upgraded memory too. So now camera has 64 meg of general memory for the operating system and 128 NAND flash. And FPGA is also somewhat larger. It's 1.2 million gates FPGA, and it has additional 64 meg of dedicated DDR memory for like temporary buffering for compression or image processing. So it doesn't share bandwidth with the system bus. With this, even with the previous camera, it was in the Linux devices article. It's where it's kind of was inspired by Gmail, where I found how Ajax application where you can make it. It still runs in the browser, but it has power of special kind of applications. So it's not. It's in the browser, but there are some. It doesn't look like just a web page. It has more. So with the camera, I tried to do similar things, and this interface is with the camera. It uses some fancy features like the translucent menus and so this web and there's some kind of magnifier, multiple. So it doesn't really look like just web page, but it is. And the only when I was making this web control page, I still had to write some C language CGI programs to run in the camera to interact with this JavaScript web page. So it was okay for me, but my goal was to make, because the camera is open, to make it accessible for larger audience of developers, to really customize the camera, to shape it into something they need. And for them, it could be difficult to go on the lower level and compile some. Because of course you can write in C programs or in C++, compile them with the for this processor, install them there, or just FTP and run from the run in the camera. But so with a new camera, I tried PHP in fast CGI mode, and it runs pretty fast. So it's not finished, because we started with just porting all the software to the new hardware, but now many features are already controlled by so from PHP, and we were in the process to make more low-level functions in the camera that can be called from PHP scripts, and so open the camera to a larger audience of developers. So I think it's. I'm done with a general description, and I'm not quite sure what parts are more interesting for you, for this audience. So maybe you can help me to with some questions. So to focus on what, because there are kind of a lot of things that I can tell about these projects, but I just not sure what part can be more interesting.
Can you talk about two things? One is multi-camera synchronization, and two is higher frame rate from the higher frame rate with high resolution.
Okay, so with the multi-camera synchronization, one way to do this is just using synchronization over the network, and so this doesn't need any additional connection, hardware connection between cameras, and because hardware connections, they normally need some optocoupling, or because if you have multiple cameras, you can get into some electrical noise problems, ground loops. So it's better to have opto isolation. In the new cameras, in the additional boards that connect to the camera, we do have these opto-isolated inputs and outputs, so that it's possible to connect. I mean, this is at a physical level of connection. Then for synchronization on the software side, again, if you do it over the network, then there still could be some latency because of the not really real-time operating system. There could be some interrupts that will lead to some latency. With the physical connection, like what we already have as opto-isolated, it goes to FPGA. So we can make it much faster, since there's very little latency, so negligible. But this again, this additional wires, additional connectors. So if the performance of the network synchronization is enough, it's better to use network synchronization. If it's not enough, then go to the additional to this additional wired connection.
Do you think we can get sub, let's say, 5 millisecond?
Yeah, I think 5 milliseconds is what we can get with just network synchronization.
How about sub-millisecond? Like 1 millisecond?
This I just don't. This needs some experiments and see how. Yeah, because I mean with the wired connection it's nanoseconds. So it's, with the network it just. I cannot. So I do not know the exact and. Okay, not a network specialist. But we can. The only way to probably to answer is just to run it and look at the statistics, see what's the spread of the latency.
Could you describe your tool chain and development flow for both hardware and software? So how your development starts with involves what tools you need, what technologies you're using?
So basically, we use now just two different parts of the software because so it's FPGA development tools and software development. For FPGA, it's FreeSMB Xilinx tools. So unfortunately, they only as FreeSMB, so we can't include them in the distribution. But at least you can go and download. I think it's like 1.8 gigabytes to download, and it includes both Linux and Windows. Even if you don't need Windows, there's no. So you probably still download all the files for Windows also, and all the FPGA code is in Verilog. You probably still need, in addition to Xilinx tools, you still need some simulator, because the simulator that you can get from Xilinx there, or Model Sim, or you need to buy a simulator, because the one that you can download, it's limited in like 500 lines of source code. It's definitely too little for this size projects. But there are free simulators that it's possible to use, and now I'm converting most of the text fixtures so to be compatible with this GPLed simulator. It can be Icarus Verilog that can, and there's also Severe that can be used to simulate chips. For the software development, it's as I mentioned before, I used Axis tools, and it was kind of one-stop shopping, or it was everything could be downloaded from SDK and compiler because Linux itself, it has support for this architecture. But of course, I mean, what Axis has, it's a little newer than what's in the main branch of Linux. So what we download from Axis is Chris compiler, is GCC Chris, and SDK that has tools for to prepare images, to flash, to transfer it to the camera, and our software is just on top of this Axis SDK. So you just so if you download the scripts, run the script, our script, it will download all the additional software from Axis, and now we use more like we use Lite for the web server. What Axis provides is a BOA, So lighting goes from other place. PHP is downloaded from php.net, and so there all the software it's automatically downloaded by the script we provide, and then just run make and get the image. If you do not want to get into FPGA design, so we provide the already so they're ready to use FPGA image. But if you are interested in FPGA design, you can download Xilinx tools and run this project and build it from source. Yeah, and then just run make file, and you will get a new image. Also, if there are some just applications to test, you don't need to build new image. You can just FTP these programs or PHP scripts or whatever to the camera file system and run it from there. And it's what we have now, but now okay. So before we used Knoppix to put all our software for the cameras, because still most users of the cameras we have, they're Windows users, and to run. So to view high-resolution video, even on Linux, we had to modify, like mplayer had some limit on the file size, frame size, the image. So we didn't get ready to use tools. We had to modify them, and of course on Linux it's easier. Also, all the kind of flashing tools, so to upgrade cameras. I tried to support some Windows version for some time, but then it depended on some third-party library that had different versions, not compatible with each other. Also, it should run on different versions. It was Windows 95, 2000, and XP, and I just gave up to support all these different versions so different versions of libraries, different versions of Windows, and the easiest solution was just to give live CD with the camera, so that runs on most computers. So you just boot it, and then you have working video player on this and tools to upgrade the software. But the Knoppix is good for live DVD, live CD or live DVD, and not so good for like a installed system. And many our customers, they ask, okay, it's nice how it runs, but it runs slow because it's from live disk. Can you help us to install software? And so now we're switching to Ubuntu to have distribution on top of Ubuntu, so to be able to run it in both live DVD mode, so to make at least to be able to have video on the from the camera, and to be able to upgrade the firmware, because this kind of special network bootloader that is in the hardwired in the processor, it needs it's a low-level Ethernet packet, so it needs some software on the PC side to be able to boot from the network. And now again, it's we're working with Canonical to make it kind of to make the distribution for the that will work with our cameras, and also to include more just general purpose tools for hardware development. And with our cameras, kind of my goal was just to have some to have development software pre-configured, like maybe we in Eclipse framework that like if you don't have experience with FPGA, you just open the project and at first you can just recompile how it is, but then so kind of to reduce entrance barrier, so to be able to play with the code without just spending too much time on getting into it, and to have the same because now what you get from Axis is just compiler, just files, so there's no IDE or so the goal is just to get it to pre-configured IDE that you with a graphical interface with some simple way to see the code, to change it, but this is not finished. We just only started to make Ubuntu-based this distribution, but this is where we're going with these software tools.
What's the limiting factor for higher frame rates? Is it the network connection? Is it the sensor in the circuitry?
Yeah, there are probably three bottlenecks. And so it's sensor itself, it's FPGA compressor, and it is the network. Actually, it's also there's bandwidth between the FPGA and the system memory. So because now we use it's pseudo DMA, so data still goes from FPGA to the DMA controller on the processor chip and then to the system memory. So to send one 32-bit wide word, you need 5 memory cycles. So and cycle is 110, so it's 100 megahertz. So it's 5 times 10 nanosecond, so 50 nanosecond per 32-bit word. Actually, the new hardware that in the new camera, this part is implemented in hardware, but it's not. There's no code yet to support it. New processor supports through a bus acquisition, so the bus control can be transferred to other devices, and all the circuitry is implemented so that just to disconnect memory from the processor, but that needs kind of careful clock switching for SDRAM memory and some SDRAM controller for the system memory in the FPGA. But so when this code will be done, you can increase this part 5 times, so the performance and the data transfer rate 5 times. So far, the only place where I hit this limitation was with Octheora, because Octheora, after DCT and quantization, it reorganized coefficients not on the single block level, but for the whole frame. And so in the beginning of the frame, you have a lot of data. In the end of the frame, it's much less. So the peak data in the beginning of the frame was too much for this DMA transfer from the FPGA to the system memory. So I had to slow down and to wait for the FPGA for the system this bus to be able to push through the data. So this is something that kind of already in the hardware, but no software support yet. And other parts are sensors. The up to 3 megapixel sensor, it used 48 megahertz pixel clock, and the camera was faster. Now we got a new new Micron chip, 5 megapixel with 96 megahertz, and now it is faster than the compressor code we have now. So 5 megapixel sensor itself can run up to 15 frames per second, full resolution. Of course, higher at the smaller window or low resolution. And current FPGA code can run up to about 11 frames per second. But these can be improved by just making some changes in FPGA code. You can put some time critical parts in parallel and get this performance. But then it will still be limited by the bandwidth of the network bandwidth, because on the new camera I didn't port yet Fiora, so it's only JPEG and motion JPEG. So it's a lot of data, but this part it limits. So it depends on the size or in bytes, not in the pixels, but in bytes. And so if it depends on the image quality, on the how many details are in the image, so how sharp the image is, this can change. So it's not the compressor has fixed pixel rate, and so currently. So it runs 125 megahertz, and pixel rate is 1/3 of this. I mean the sensor pixel rates, because of the color. So if it's run in a normal mode, it's YCBCR 420. So for each 4 pixels, input pixels as bare encoded, you get 6 pixels for the compressor to compress. And actually the hardware can run, I mean the current hardware can run up to 160 memory and FPGA 160 megahertz, and with this it's so pixel rate is 1/3. I mean the sensor pixel rate is 1/3 of 160 megahertz, but and this we will change to get full speed of the 15 megapixel sensor. It's not that far, and just some parts to put in parallel. And
any more questions? We thank Andrey.
Okay.